Is the 10th. And we'll get started anyway. I know we're not going to finish this one, but we'll get a good jump on it. According to the syllabus, today we're going to start stress transformations. Gosh, what chapter? I can't reach my textbook from where I'm sitting, but I think it's chapter 8. It could be chapter 9. Chapter 9, thank you. Okay, so chapter 9, we're going to talk about stress transformation. This gets a little technical. There's a lot of little elements and there's some trig, and this gets a little techy. So I think it's good that we just have like an introduction to this, and then we'll have some more time to go through this. The basic premise of this, and here I could just kind of draw something on there. Remember when we were talking about normal stresses and shear stresses, which stress is a force over area, right? And we had this block. Mustafa, curving the exams. I don't curve this exam explicitly or the first exam explicitly. What I do is I gather all the data after everybody has taken the final, and then I curve the class accordingly. I curve each of the 3 exams independently because there may have been something on one exam that I just totally blew it and didn't talk about at all. Okay, you guys are, okay. Where was I? Curving. I curve each one of the 3 exams independently so that if there's something that I blew on one of the tests, it will curve it up and make it more fair to everybody. And then I then take the curved grades and find out everybody's final grade. But my curving mechanisms don't work until I get all 3 tests into the system, and then I curve it. So I don't know exactly where everybody is until after I've graded the finals. But that's how I curve those. Uh, yes, I will be posting this lecture PowerPoint. I had planned on spending more time on the exam because the last exam, we took the whole time going over the exam. So I wasn't sure I was going to get to this lecture or not. But tomorrow I will post this, and this will be the same lecture that we will continue on Thursday. Okay? Where was I? Okay. We had talked about a block of wood. And if you just put a tensile force on the block of wood, remember this one? And just a tensile force on a block of wood with a plane that is perpendicular to the block, all you have is normal stress. There is no shear stress. So you would look at this problem and say, well, there is no shear in this element. It's all pure tension. But then we said, well, wait a minute. What if you cut a slice this way and you sum all your forces on this plane? Then we found that we had some tensile forces, yes, but we also had shear forces, shear stresses. And the magnitude of the normal stress and the magnitude of the shear stress depended on the angle that we were looking at. So we could find a shear stress like this, or a normal stress like that, and we could find a shear stress like that. And as you rotated this shear plane, you get different magnitudes of shear stress and normal stress. That's what this is all about. Now we're going to do a rigorous treatment of rotating our coordinate axes to see what it does to the shear stress and the normal stress as you rotate through different angles. Okay, so starting with I have a kind of a technical, rigorous approach to this, starting with a little cube of some material that we've pulled out of a structural member. And we're going to label the axes as so. I got my x-axis, my z-axis, my y-axis. In 3 dimensions, there are 3 independent normal stresses, sigma x, sigma y, sigma z. You actually have 6 sides to the cube, obviously, but the opposite sides are not independent. They are the opposite of these normal stresses. We're going to come up with a subscript that follows the axis direction. So our nomenclature is normal stress sub y is parallel to the y-axis, x is parallel to the x-axis, z is parallel to the z-axis, right? So far, so good. Stresses on sides not shown are just equal and opposite in direction as to ones that are shown. Now, in 3 dimensions, we also have 3 independent shear stresses, which is kind of interesting. You got 6 sides. Each side can have shear stresses in 2 directions, but there's still only 3 independent shear stresses, not 12. So as you can see from this diagram, and kind of parse this out a little bit, this shearing stress here is equal in magnitude to this shearing stress here. They have to be, or the element would not be in equilibrium. I can illustrate that a little better. If I'm looking at a section right through the middle here in the z, y plane, then this tau zy is here, and this tau yz is here. And then the other 2 sides not shown are equal and opposite in direction. So that would be here and here. Now, if I sum my forces about some point in the middle here, if all 4 of these vectors are not exactly equal, then this cube's not in equilibrium. So that's why tau zy has to equal tau yz. And same on the other side here. So instead of 4 independent shearing stresses, you really only have 1 independent shearing stress. And so you have 1 in the YZ plane, you have another 1 in the YX plane, and the third is in the XY plane. So that's why you'll have 3 independent shearing stresses. Okay, so tau xy is equal to tau yx, tau yz is equal to tau zy, tau zx is equal to tau xz by the definition or the explanation that I just gave you. The subscript notes direction of the normal, and the second subscript notes the direction of the shear. So let's see, did I do the limiting discussion? Nah, let's go back one. Okay, so this shear vector right here, tau zy, the first subscript denotes the normal direction of that shear. So that shear is in the z plane, or the plane that is normal to the z-axis. So the z is the first subscript denoting that this is lying in the plane that is normal to the z-axis. This guy over here, tau zx, is also in the same plane. So that's z and z. The second subscript is the direction of the shear. So this is pointing in the y direction. This dude is pointing in the x direction. So that's how we get our subscripts. For like instance, this guy right here, tau xy, it is in the x normal to the x direction, and it is pointing in the y direction. Any questions on that? Okay, so to make this a little easier on our eyeballs and our brains here, we can limit our discussion to a two-dimensional plane, just so that we can establish some principles. We're going to limit it to a two-dimensional plane. So our two-dimensional plane only has normal stresses in two directions, sigma y, sigma x, and we only have one independent shear, tau. Remember, tau xy is equal to tau yx. So the shear on all four sides of our cube now are all equal. And we have the same nomenclature. Tau yx is in the normal to the y direction, pointing in the positive x direction. If we slice our cube and look straight down on it, we have a two-dimensional square in the xy plane. Okay, so I'll go back one and just kind of freehand this a little bit. If I make a slice this way and I look straight down, then this is the coordinate system that we're working with. Okay, so the positive x is to the right, the positive y is up in this case, and this is, like I said, we're kind of reducing this to a two-dimensional problem so that we can get our hands around some of the more complicated concepts here. Okay, so we can place a sigma x in the x direction. We can, the sigma x acts on the opposite face in the opposite direction. If sigma x is positive, then that means it's tensile. As I've drawn it, this would be a tensile stress trying to pull the element apart. We can place the sigma x in the minus x direction. Okay, we did that. We can add sigma y in the y direction. This is a positive sigma. This is, again, in tension. And sigma y is completely independent of sigma x. So sigma y can be any value, sigma x could be any other value. They're not tied together. And then by summing forces in the y direction, we find by equilibrium that sigma y acts on the opposite face as well. So these are my positive sigmas, my normal stresses. We can play, yeah, we did that, okay. Now, if you have shear that acts on the element, we can add it in the xy direction. So this is a positive shear. Why is this positive? Because it is, x is normal to the x axis, y means it's pointing in the direction of the positive y direction. And because it is positive, or it is pointing in the same direction as positive y, then it is a positive shear stress. If it was pointing the other direction, it would be negative. We place tau xy on the face of x normal and pointing in the positive y direction. By summing forces in the y direction, we find by equilibrium that tau xy acts on the opposite face in the opposite direction over here. We place tau xy in the minus y direction. Summing forces about a corner with the red circle. So if I sum my moments about here, sigma x on each face cancels each other because it has the same eccentricity, as does the sigma y's cancel each other because they each have the same eccentricity and they are opposite in direction. Tau xy on the left face has no moment arm, this one, but tau and a xy on the right face does have a moment arm of the width of the element. Therefore, tau yx must be added to balance tau xy on the right face. So we need this tau yx to equal tau xy with the same eccentricity to maintain equilibrium. Finally, tau yx must be added at the lower face to balance the tau, that's supposed to be yx on the top face for the sum of the forces in the x direction. By maintaining equilibrium of the element, we see again that tau xy equals tau yx. When we were talking about shearing stress and we were talking about horizontal shearing stress, we saw this as well, that the vertical shearing stress and the horizontal shearing stress at the same point on the beam are equal in magnitude. Any questions so far? Okay. So the stresses found are valid for the chosen reference system, X and Y. The dotted, what color is that? Kind of a yellowish tan. The dotted yellowish tan are my grid systems, X and Y. But we need a way that we can solve for our stresses. When I say stresses, I mean sigma X, sigma Y, and tau XY. We need to be able to solve for these stresses at any rotated coordinate system. So we need a transformation system to transform the stresses that you see here into a rotated stress condition like this. So if we rotate the element by some theta, and here I'm showing a positive theta rotation of the x-axis, then we create a new coordinate system of x prime, y prime. You guys, pardon me for just a second. I need to close my office door. Sorry about that. Everybody still there?
Yes, we're here.
Awesome. Okay, so hopefully without getting into too much of the mumbo jumbo, everybody sees the point of what we're trying to do. What is the overall concept? What are we trying to do? And what we're trying to do is if we have found the stresses on a Cartesian coordinate system, X and Y, then at any other coordinate system rotated through some theta degrees, can we find the transformed stresses on this alternate coordinate system? That's the overall point of what we're trying to do. Okay, so to start this, the formulation of the stress transformation equations, we're going to define an area A of a, I'm sorry, we're going to define a rotated area delta A. Sorry, that's not, this is a variable. This one is just a rotated area. So we're going to do a slice right through this rotated coordinate system along our y prime. And we're going to find what the area is in the resultant directions along x and y, my original x, my original y, my areas of this area. So then we can define the components of delta A. So delta A is this rotated area of the element, and the vertical component is delta A cosine theta. The horizontal component is delta A sine theta. So just basic trick. Taking a free body diagram of our inner slice, we can find the forces on each of the three sides. So here's my inner slice. This is my slice along Y, the vertical component, the horizontal component. Okay, so sum the forces, actually before I do this, how did I get all this? So I have a sigma x prime times delta A. That's the force along x prime. Sigma x prime, we don't know what that is yet, but that is the stress along the x prime axis. Tau xy prime, we don't know what that is either, but that is the shearing stress along the parallel to the y prime axis times delta A. Remember, a stress times area is a force. So this is my shear force. This is my normal force along my cut plane. And then over on the other side, for equilibrium, starting with the horizontal, I have my original sigma x times delta A cosine theta. So the stress is sigma x because that's what we started the problem with, was a horizontal stress of sigma x. This area is the delta A cosine theta. This guy here is my original shearing stress, tau xy, times the area, which is delta A cosine theta. Down here, I have my horizontal shearing stress, which is tau yx, my original shearing stress, times this area is delta A sine theta. And then lastly, the vertical is my original sigma y times this area delta A sine theta. So here I have a system of equations where I have my unknown sigma x prime, my unknown tau xy prime, and it is in relationship to a known sigma x, tau xy, tau yx, and sigma y. Let that soak in for a second. We've just created a free body diagram, and we're able to use this free body diagram with two unknowns described by three knowns, known values. Okay, so now we can sum our forces in the x prime direction. So I'm going to sum all the forces in this direction. This is where it gets a little interesting. I have in the positive x prime direction, sigma x prime delta A, that's here. I have in the negative x prime direction, so minus, and what I have is tau xy, this vector here has a component in the x prime direction, and that component is cosine theta. So I have the force is tau xy delta A cosine, oops, I'm sorry, I'm using this one. Sorry, starting with this one. My force is tau yx delta A sine theta, tau xy yx, same thing, it is a typo, but tau xy delta AS sine theta is this force, and then the component of that force in the x prime direction is cosine theta. Okay? Minus, now we've got sigma y delta A sine theta is this force, and the component of that force in the x prime direction is sine theta, and I got a tau xy delta A cosine theta, that's this force, and the component in the x prime is sine theta. And lastly, I have my sigma x delta A cosine theta, that's the force, and the component in the x prime direction is cosine theta. Pretty ugly, huh? Any questions on where the terms are coming from? Okay. It looks nasty only because the stress times the areas are described as a component of the original area. That's the sine, sine, cosine, cosine. Then each one of these forces has a component in the x prime direction. And for that, I need another cosine, sine, sine, cosine. So it's just starting to look a little ugly. But we can clean it up, right? So first thing that happens is the delta A washes out completely. There's a delta A in every one of these terms. So we just divide the whole mess by delta A and it washes out. Then we have a sine cosine. We have a sine squared, a cosine sine squared, and a cosine squared term. So I collect all the terms. So I have sigma x cosine squared, sigma y sine squared, and both of the sine cosines were tau xy. We've already stated that tau yx equals tau xy, so we just stick with tau xy. And then you have two of them, and they're sine and cosine. So this cleans up very nicely. And we can see what the goal is. This is the overreaching goal, is that we're trying to get to what is this stress, normal stress along the x prime axis as described by the original stress in the x, y shear, and the theta angle between the original axis and the new axis. Okay, likewise, we can sum all our forces in the y prime direction. And we have the same number of terms, only this time we have tau xy here, tau xy times delta A, that's this term. And then we have, actually this guy drops out completely. There's no component of the sigma x prime delta A in the y prime direction. So this guy does not appear at all. And then each of the other four, 1, 2, 3, 4, each of the other four, the force has a cosine or sine in it. And then the resultant of the force in the y prime direction has another sine or cosine to it to render this result down here, which is similar to this one. We just collected the terms. And what we find is tau x prime y prime, the shear parallel to the y prime axis, is described by sigma y minus sigma x times sine theta cosine theta plus tau xy times cosine squared theta minus sine squared theta. Okay, so we can simplify.
Could you go back one, Professor?
Sure. There?
Yeah. All right, thank you.
So simplifying, using some trigonometric functions, we can say that sigma x prime is sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times cosine 2 theta plus tau xy sine 2 theta. If the problem statement, again, gives you sigma x, sigma y, and tau, then you can just plug all this in and solve directly for sigma x prime. Sigma y prime is sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine 2 theta. And lastly, tau xy, x prime, y prime equals negative sigma x minus sigma y over 2 sine of 2 theta plus tau xy cosine 2 theta. So these are the sets of equations that we're going to use to solve for these. And I think this is a good point to stop with example number 1.
Professor, could you go back one more? Sorry.
This is lecture 22.
Thank you.
Slide 50. Okay. Any other questions for tonight?
Can you go back to the components again?
This slide or further back?
Yeah, this one.
Okay. Yeah, give me till tomorrow morning, but I'll take this PowerPoint and I'll put it on Blackboard for you guys for tomorrow. Okay, any other questions for tonight?
So, Professor, for f of y prime, why did you say that the stress x prime times a delta a will cancel out?
This guy, it doesn't cancel out. It's just that this is aligned with the x prime axis, and we're summing all forces in the y prime axis, which is by definition 90 degrees.
All right. Okay, that makes sense.
Okay. I got a private question here. Oh, today's Tuesday. I'll just, somebody had asked me to post homework number 12. I will do that right now before I leave, so that homework 12 is due next Tuesday, a week from today. Thank you for reminding me. And if there's no other questions, I will end this for tonight. Thank you, everybody.
Thank you, Professor.